Welcome back. So we've seen two different ways to format our data for using with a pre-trained model, and that's automatic transforms and manual transforms. Now let's figure out how to get a pre-trained model. How do we load one in? So getting a pre-trained model. And so we'll write down here, there are various places to get a pre-trained model, such as we have one is PyTorch domain libraries. Two is libraries like TIM, which is Torch image models. I'll just put that in brackets. Torch image models. And then we have three, which is Hugging Face Hub for plenty of different models. And then four, another place is Papers with Code, which is going to be machine learning research papers for models across different problem spaces / domains. We're focused, of course, on just pure PyTorch, but you've also got these other things. So yes, there are places to get a model, but how do you choose a model? That's an important step. That's really the million-dollar question. Which pre-trained model should you use? Now, there's no definite answer to this. So like much of machine learning, I'm going to encourage you to adhere to the machine learning practitioner's motto of experiment, 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 to try and find out which model best suits your problem. But what do we want to do? What's the whole idea? The whole idea of transfer learning is to take an already well-performing model from a problem space similar to your own and then customize it to your own problem. And so when I pick a model, there are usually three things that I consider. Three things to consider. One is speed, because a slow model is not really a model, right? We want things to work fast. Two is size. Three is performance. And they're usually tied all together, right? Speed, size, performance. So speed is how fast does it run? Size, how big is the model? Once a model gets pretty big in terms of number of parameters, you need a specific set of hardware to store that model, and performance is how well does it go on your chosen problem. E.g., how well does it classify food images for our problem of Food Vision Mini. So speed, let's think about this, right? If we had a Tesla car, images. Do we have self-driving on here? Tesla self-driving. So here, a Tesla model, the model needs to be quite fast because you're driving. So if you had a slow model while you're driving, that's not really a good thing, right? So Tesla have to consider how fast their model needs to perform on the car. And so another thing to consider is if we look up compute server, two kind of real ways to deploy a model is by storing it on a compute server. And then what would happen is the Tesla car might take a video of the scene, upload that to a compute server, and then the compute server would send patterns back to the car. Now, just think about that. Would that work in a driving space? Well, it wouldn't really, because you can't really wait for that time to upload the video to the compute server and then download it back to the car. So the model needs to be on the car. So that's something you'll have to consider is where does the model live? Is it on device, as in like a self-driving car, because you need it to be fast. You can't have it upload, self-driving car. Or does it live on a server? These are kind of all tied together, right? You want the fastest model you can at the smallest size you can with the best performance. Does that make sense? The fastest model you can get, at the smallest size you can get, at the best performance. Now, of course, there's no real silver bullet here as the most ideal model, but these are just things to consider. What is your problem? So for Food Vision Mini, if we wanted to deploy our model to a mobile device, we'd want it to run fast. We'd want it to be relatively small so that it can fit on a mobile device. And the performance would have to be pretty good, otherwise people won't use our model. So that's just things to consider. And so if we go into looking at, we come into here, say we've got a whole bunch of array of models that we could choose from. I'm just going to close all of these tabs so we don't get, there's a lot going on here. But that's all right. It's going to all come together. Things to consider. We're working on a classification problem. Let's keep our ideas in mind. Speed, size, performance. So if we scroll down, we have table of all available classification weights. So these are pre-trained models. How do we choose one of these? I'm going to bring this in. Looking at this, which model should we choose? So let's keep our 3 parameters in here. Speed, size, performance. So Food Vision Mini, we want to run it on a mobile device. That's our criteria. So we need a fast model, we need it relatively small, and we need good performance. So if we look at all these, I'm not going to go through all of them. You can do that as extra curriculum. But look at all these pre-trained models. This is the beautiful thing about machine learning is most of the best research gets open source. So where's EfficientNet? Or let's just look at this. So the weights, these are the different pre-trained model weights. Most of them are on ImageNet 1K. This is their accuracy value. So this is the performance. How well does a model classify certain images? And then the parameters here is the size. And you can kind of say that if the parameters is relatively small, it should be fast. It's not always the case, but generally, the less parameters, the faster they run, because a parameter is essentially a computation that you have to go through. So the higher number of parameters, the slower the model is going to run in terms of inference, in terms of making predictions. Generally, not always the case, but just generally. So in our case, we'd look for the best trade-off between highest accuracy and lowest parameters. Now you could go through all of these and figure it out, find the highest accuracy to number of parameters ratio. The reason why I choose EfficientNets is because they are generally very good in terms of performance with a lower number of parameters. For example, look at EfficientNet B0 weights. We have, let's just call this 78% accuracy with 5 million parameters versus, let's find another model. Inception V3, we have less accuracy than EfficientNet B0, but 6 times as many parameters. That's something to keep in mind. Then if we scroll down, we have other models. What's a similar, where's 78? 78, 77, there we go. RegNet X, these model names can get creative. Okay, this is pretty close to EfficientNet B0, but you could keep going through this. So for our criteria, we want best performance with lowest number of parameters. So EfficientNet B0, and then another thing to consider, if you wanted a mobile specific device, a specific model, there's also the concept of mobile nets. So these have quite a good accuracy performance, not as high as EfficientNet B0, but a low number of parameters. So if we look at MobileNet V3 large, we've got 75% accuracy versus EfficientNet B0, which is 78 thereabouts, rounding up. And we have quite the same number of parameters. So that's just something to keep in mind. When you're choosing a model, you want speed, size, and performance. For our case, it looks like FNet B0, EfficientNet B0 for short, or FNet B0 for short, is one of our best options in terms of performance versus size. And so we're going to set this pre-trained model up in a second. I just want to introduce you to one more important thing, which is a great essay in the world of AI. However, for our case, let's just say our use case, our end case is deploying Food Vision Mini on a mobile device. So we have a compute restriction because an iPhone doesn't have as much compute as, say, internet server. However, in light of the bitter lesson, I'm going to show you what this is in a second. If we had infinite compute, we'd likely pick the biggest model plus most parameters we could, plus most general. That's another thing to consider. We could. And so the bitter lesson is one of my favorite essays in the world of AI. I'll let you read this. The bitter lesson. So the biggest lesson that can be read from 70 years of AI research is that general methods, so the more general the method, so a neural network is considered a general method, that leverage computation, so as much computation as you can get, are ultimately the most effective and by a large margin. So I'll let you read through all this, but my main takeaway from this is that generally, the more data you have, the more compute you have, the more general your method, such as a neural network, a learning algorithm, the better your results will be. So if you had infinite compute, go for the biggest model you can. But we don't. We're keeping things small and we're scaling up when necessary. So that's which pre-trained model you should use. Keep in mind your speed. How fast does it need to run? Does it need to run? Are you deploying it to a device and it needs to run on that device, or can it run on a bigger compute, say in the cloud, on a server? How big is the model? What kind of hardware do you need to store it? Because the bigger your model gets, the more advanced the hardware needs to be to store it. And what performance do you need? What's the minimum level of performance you need to get out of your model, out of your chosen problem? So for our Food Vision Mini, we probably want it classifying images at close to 90 or 90+% accuracy. For a self-driving car, you probably want even higher than that. So keep these three things in mind. For your extra curriculum, go through here and find out, is there a better model than EfficientNet B0 in terms of accuracy and parameter ratio? If there is, let me know on the GitHub discussions. Otherwise, I'll see you in the next video. Let's see how we can set up our very own pre-trained EfficientNet B0.